lecture series on complex analysis for undergraduate students. Today's lecture is an application of Cauchy integral formula. In the last lecture we had seen one application, that evaluation of integrals. Today we will go for the more applications in the analysis as well as with their help how to evaluate certain integrals. So let us go with the first application, the derivative of analytic function. With the help of Cauchy integral formula we will prove one important result, that analytic function has all the derivatives or all order derivatives and they are also analytic. So here I am giving you the result. If fz is analytic within and on a simple closed contour C or in a domain D, and if z naught is any point interior to C, then it has derivatives of all orders in D which are also analytic. The value of derivative at point z naught is given by the formula, the derivative of f at z naught as factorial n divided by 2 pi I integral on the closed contour C fz upon z minus z naught to the power n plus 1 with respect to z. So when I am talking here the domain D, I would mean is that is the domain containing the points on C and interior to C. If the function is analytic within that interior and on the contour, then it will have at all interior points will have that function would be analytic, and the formula for the derivative at that point could be given as the integral of this one. Let us see that is how we can obtain it. So first we will go for proving this result using the Cauchy integral formula. First we will go with the first derivative and then second derivative, and then we will just see is that is in the we could find out this formula with the induction. So let us move to the proof. Let us say this is a domain. So when I am talking about D, I am not talking about this complete one, I am talking about in the statement of the theorem the points on C and inside this one. So let us see is this is a contour and z naught is a point inside this contour C. So what we are saying is we would just start with this Cauchy integral formula. If I take the integral along this contour of the function fz upon z minus z naught, by Cauchy integral formula it is 2 pi I fz naught, or fz naught is 1 upon 2 pi I integral on this closed contour C of fz upon z minus z naught. What is this contour C? This contour C now I have taken as one you could say is looking like a circle with the radius d, but it is not actually, it could be any contour C. Now this Cauchy integral formula I would apply to any other point fz naught plus delta z. So what we do is I take one point z naught plus delta z in a small neighborhood of this z naught. That small neighborhood of z naught, if I do take the point z naught plus delta z, so that is small neighborhood I have taken in a manner such that that is also inside this contour C. So again using the Cauchy principal formula for that point, I could write that fz naught plus delta z as fz upon z minus z naught minus delta z dz integral along the contour C 1 upon 2 pi I. So now the difference of fz naught plus delta z minus fz upon delta z, I would write that is 1 upon 2 pi I integral fz upon z minus z naught minus delta z minus of fz upon z minus z naught. So this is what we are writing. So for this fz naught plus delta z, this is integral fz dz upon z minus z naught minus delta z, and for fz naught, it should be fz naught, it is fz dz upon z minus z naught, where I have taken z naught plus delta z in a small neighborhood of z naught, such that this z naught plus delta z is also inside the contour CR, is also interior to C. Now from here if I just write, because this is the same contour, so this integrand we can join and we could get it after simplifying it. I could write it out, that is fz upon this one we would get is it is only delta z upon z minus z naught delta z into z minus z naught into fz. So delta z and delta z, that is getting cancel it out, and I am getting it is equal to 1 upon 2 pi I integral along the contour C of fz upon z minus z naught minus delta z into z minus z naught with respect to z. What we will go is, we will first show that the limit of this is given by the formula, that is 1 upon 2 pi I integral along the C fz upon z minus z naught square dz. So that we could show that this limit of this function is that. So we could show that by the definition of derivatives, that the derivative of this does exist, hence it would be analytic at z naught. So we will go in that manner. So let us just write it out what we want. We will write fz naught minus delta z minus fz naught upon delta z minus 1 upon 2 pi I integral fz dz z minus z naught square. So this function we had already find out that this is equal to this integral minus, I am subtracting this integral is again on the same contour, 1 upon 2 pi I is common. So again what we do have is integrand is here fz upon z minus z naught minus delta z into z minus z naught, and here the integrand is fz upon z minus z naught whole square. So if I take the difference, I would again get the difference as delta z upon z minus z naught whole square, z minus z naught minus delta z. So what we would get is 1 upon 2 pi integral along the contour C fz z minus z naught minus delta z, z minus z naught minus fz z minus z naught whole square dz. Now let us do find out this absolute value of this difference is delta z upon 2 pi I fz upon z minus z naught minus delta z into z minus z naught whole square. Now what we would like to show is that this integral should go to 0, so only then we would be able to say that the limit is existing. So we are going to prove that as delta z is small enough, that is from z naught to delta z, z naught plus delta z, if delta z is small enough, this integral goes to 0. For doing it we would again use this ML inequality to find it out, that is how we are using this Cauchy integral formula and this ML inequality. Fz is analytic, so Fz would be less than would be bounded, because Fz is analytic inside this. So I could find out one point that is such that Fz naught is less than m, because it is a continuous. So in this neighborhood I could find it out that it is less than m. That is a very simple result we have done many times till now. Now since z minus z naught any point on this C is greater than d. Now d I am taking some distance, or you could say as d is the smallest distance from z naught to this contour C. Then for any z on this contour C, z minus z naught would be greater than d. This says is z minus z naught minus delta z, that is z naught plus delta z, suppose this is the point here, would be greater than, just using the absolute value inequalities, would be greater than or equal to modulus of z minus z naught minus modulus of delta z. Z minus z naught modulus of this is greater than d, hence this would be greater than or equal to d minus mod of delta z. Now what it says is my fz is less than m, z minus z naught is greater than d, z minus z naught minus delta z is greater than or equal to d minus delta z. If substitute all these things, what I would get, this integrand fz upon z minus z naught minus delta z into z minus z naught square would be actually bounded by m upon d square into d minus mod delta z. So now what we do get is this would be less than or equal to delta z upon, that is m is this one, m upon d square into d minus delta z. This delta z is as such here, and L. What is L? L will be the length of this contour. Now, whatever be this L, this is fixed one because this contour C is fixed one. So, this L is fixed one. Now, if delta Z is small enough, what I would get is that this would go 0 and this is again a fixed quantity, M is a fixed quantity, L is a fixed quantity. I could make this delta Z such and small such that it approaches to 0, or what we are saying is the left hand side. This is the absolute value of this integral, this has to be positive, or you could say is non-negative. This is less than or equal to a value which can be made arbitrarily small, such a small that it can move to 0. So, this must be equal to 0. If this is equal to 0, then what we have got by this definition of now, we had proved that fz naught minus delta z minus fz naught upon delta z, which is minus 1 upon 2 pi I integral C fz upon z minus z square dz. That is what this absolute value difference was from the last slide, if you do remember. This is by the definition of integration or this differentiation. This is nothing but the f dash or the derivative of f at z naught. So, this is equal to this one. So, what we had proved is that Cauchy integral, from the Cauchy integral formula, that if f is analytic in a domain D, then f dash, or that is f is dash z is there, and f dash z naught is again we are getting in the form of this integral. You see, f of z naught, we had started f of z naught as the form of integral using the Cauchy principle, the Cauchy integral formula, that 1 upon 2 pi I integral over the closed contour C f z upon z minus z naught. That was where f z was analytic. Since f z was analytic, we had shown that now this function we are getting is, that is f dash z naught is this one. Now, f dash z naught is again coming in the same form. The only thing is that is here we had made it z minus z naught whole square rather than z minus z naught only. Function f z is analytic again in the whole domain D, in the contour C and inside this C. Only point of discontinuity or this where this analyticity would break for this function f z upon z minus z naught square would be only z naught. That is again the same kind of conditions are being satisfied. So, in the similar lines, if I move, that is if I again take f dash z naught minus f dash z naught plus delta z using this formula, and then use it factorial 3 upon 2 pi I and like that one, you would get it that this is again going to prove, that is you would get that this limit is going to 0, or you all will be getting is that the formula would be satisfied. The only thing is that is you have to use the distance, the minimum distance of z naught to the contour C that we had already used. In the similar manner, you can move with certain modification, small modification, that is how to get it these points, you will get it square and cubes and all those things. So, here you will get cube and these points as such. So, we would get that is f dash z naught in the similar manner is also analytic, and the formula for f dash z naught we would get it like this one. What we are getting is actually z naught, the point I have taken any arbitrary point in the interior of C. What it says is, if fz is analytic in this whole region, then for any z which is interior to this C, because z naught was arbitrary, I have not chosen any particular z naught. So, for every interior point in this region, fz would be the formula would be given by the same kind of thing for any z, and since z naught is arbitrary, what we do say is f dash z will also be analytic in whole region. In a similar manner, we will go again for that f double dash z. So, what we are getting is, because z naught is arbitrary, we are getting that if fz is analytic in a within and on a simple closed contour C, then its all ordered derivatives, that is first order derivative, second order derivative and in a third order derivative, they would be existing and they would also be analytic, because all of them we would be getting is in the form of this integral formula. So, we had proved this result that this would be analytic and this one. So, now let us see that is how this formula or this theorem is going to helpful in evaluation of integrals. Let us say evaluate the integral on any simple closed contour C enclosing pi I of this integral cos z z minus pi I whole square dz on a closed contour C, which is any closed contour C enclosing pi I. So, let us see this. Suppose this is a closed contour where this pi I is the interior point. Now, I would use this analyticity of the fz and what we have got that formula that f nth derivative of z, or rather you could say just I would use f dash z naught is equal to 1 upon 2 pi I integral along the closed contour C of fz upon z minus z naught whole square dz. Here you see what the condition I do require is that my fz has to be analytic in the whole region, that is inside the C and on the C. Now, I am taking any simple closed contour. Now, let us see what is this function cos z. Cos z is actually an entire function, and that is why if I do take any simple closed contour, it does not matter because it is entire function. So, till it is or until it is containing this pi I as interior, this result would hold true. So, f dash z naught 1 upon 2 pi integral along this contour C f z upon dz z minus z naught whole square. So, now what is f dash z naught? F z is cos z. So, f dash z would be minus sin z. So, at z naught is the point pi I. So, I would get it minus the 2 pi I minus sin and at pi I. So, this is 2 pi sin hyperbolic pi. So, you find it out, that is we could evaluate this integral using this formula for the derivatives. Let us see some more examples. Evaluate the integral on any simple closed contour C enclosing minus I for the function z square minus 3z square plus 6 upon z plus I cube dz. Now, you see this integral of this function, the function which is on the numerator z to the power 4 minus 3z square plus 6, this is a polynomial, we do know that z to the power 4 z square, all these are entire functions. So, this is an entire function, that is why we are able to do it in general, that is any closed contour enclosing I. So, let us see, this is the closed contour and which is having minus I as to the interior of this one. Then here what I do have is z plus I cube, that says I have to use the second derivative formula. So, this is an entire function f double dash z of this. If I do find out, that is f dash z would be 4z cube minus 6z square, it is again derivative, I would get 12z square minus 6. The formula what I would use is f double dash z naught is 1 upon, that is 2 upon 1 factorial 2 upon 2 pi I, that is 1 upon pi I integral along this contour C of f z upon z minus z naught cube dz. Now, here the z naught is now my minus I. So, what I would get is from here this integral, this function is f z is z to the power 4 minus 3z square plus 6. So, I would get this integral as pi I times f double dash z naught, that is 12z square minus 6 evaluated at z is equal to z naught, that is z is equal to minus I. So, when I keep z is equal to minus I would get here minus 12 and this I would get as minus 6. So, minus 18. So, I would get the answer as minus 18 pi I. Let us see one more interesting example. Evaluate the function e to the power z upon z minus 1 whole square into z square plus 4 integral of this function along the contour C, where my contour C is actually an ellipse whose this x axis is going from minus 3 to plus 3, and or you could say that is a function which is having the other points of not analyticity outside, only point which is where this function is not analytic, that is only one is the interior, and the point 2i and minus 2i are not interior to the closed contour C. So, I am having this contour C where 1 is interior, but this 2i and minus 2i both are outside this one. So, now I will choose this function e to the power z upon z square plus 4. Of course, e to the power z is entire function, but when I take e to the power z upon z square plus 4, it will not be analytic at plus minus 2i, but from the given contour I am finding it out that plus minus 2i are outside our domain D. So, this function e to the power z upon z square plus 4 is analytic inside and on the contour C. I would like to use this z minus 1 whole square. So, 1 is inside this one. So, I would go with the first derivative f dash z of this one would be e to the power z square plus 4 minus 2z into e to the power z upon z square plus 4 whole square. So, f dash z naught using this formula again 2 pi I integral along the contour C f z upon z minus z square dz, where z naught I will take as 1, I would get this integral as e to the power z square plus 4 minus 2z upon z square plus 4, it should be whole square at evaluated at z is equal to 1. This is your evaluated at 1, you will get it 6 e pi over 25 I. Now, here what we have done is that we have taken analytic function on a simple closed contour and inside that one, that is we have talked about the derivative of the analytic functions inside a closed contour and on the closed contour. Let us make this result little bit more general. Let us talk about the functions defined by the integrals. Let C be any curve and GS is a continuous function on C. Now, define a function G, capital G, as the integral of GS upon S minus Z with respect to S on the this path C, where this Z is not on the path C. So, let us see, that is what I am saying is, suppose C is any curve. So, I am not talking about simple closed curve, it is any curve, and the orientation let us say is that is this manner. Then we are defining and we are having G, which is not an analytic function, we are having it as a continuous function on this curve C. And now I am defining one more function capital G on capital G at a point Z, which is not on C, that is any other point here Z I am taking, and I am defining it the function at this point using the function on this path integral of this. So, we are saying is GS upon S minus Z ds on this path integral for any Z which is not in C. Now, if I have defined this one, now what I would like to say that this function capital G, which we have defined as the integral of this one, this is actually analytic, and if this is analytic, its all other derivatives are existing and they would also be analytic. So, we are now moving a little bit further, not on any simple closed curve and not starting with this function f to be analytic in that domain. We are starting with any continuous function g. So, for that let us have to another point, say in the small neighborhood of this z as z naught plus delta z. So, by this definition which we had made, at this point also I could this point the function would be again the integral along this path of gs upon s minus z minus delta z. So, this would be because this z plus delta z is also outside this path c. So, it is gs upon s minus z minus delta z ds along this path c. Now, what I will again go with the first definition of the derivatives, and I will show that is gz plus delta z minus gz, its difference divided by the delta z should go to some limit, and that limit must be the derivative of this function. So, that limit we will find out again the form of integral. So, let us first move this, the difference of function g at z plus delta z minus that function g at z divided by delta z. So, this 1 upon delta z is as such, this difference of these two integrals. So, I would write it as integral on the path c, this gs is taken common, and what is being here is 1 upon s minus z minus delta z minus 1 upon s minus z. Simplify it, I would get s minus z minus s minus z minus delta z, that is would get here delta z upon s minus z minus delta z into s minus z. So, we would get 1 upon delta z gs s minus z minus delta z into s minus z and delta z. So, that delta z and delta z would cancel it out, and I would get that g of z minus g of z plus delta z minus gz upon delta z minus integral c of gs upon s minus z square ds. Now, you see is that is I am just moving in the same manner as we have moved for the analytic function f, where we have taken is 1 upon 2 pi I factorial n upon 1 upon 2 pi I f z upon z minus z naught to the power n plus 1. So, I am moving the same one, that is only thing is that constant 1 upon 2 pi I is not here. So, we just want that is this in derivative of this function must be this function. So, let us just take this one. This one we had find out that this was also integral along the path c of gs upon s minus z minus delta z into s minus z. So, now if I do write it out, I would get it as 1 upon delta z path integral along the path 1 upon s minus z minus delta z into s minus z minus s minus z whole square gs ds. Again simplify it, what we would get? We would get delta z ds upon s minus z minus delta z s minus z square ds. That says is that now the difference between these two is this integral. What we have to now show? We have to show that as delta z approaches to 0, this integral must approach to 0, so that I could say is that the limit of this function is as delta z approaches to 0 is this function or this integral, so that we would establish that the derivative of this g capital G is this function, and so this is analytic at any point z. So, now let us move to this one. Here what we will say, we have taken that G is continuous on this path C. Now, let us assume, because this is some fixed path, let us assume that for some s on this path C, my G would attain the maximum value, or you could say is M is the maximum of all these points on the path C. So, then Gs would be less than this capital M for all s on this path C. Moreover, let us just take the shortest distance from this Z to this path C as the D. What it says is for every s on this G on this C, the difference from the s to Z should be greater than D. Since I have taken this the shortest distance from z to this path C. So, z minus s must be the absolute value of the distance between z and s must be greater than d for all s in the C. Now, if I take s plus delta z, s plus delta z is in a small neighborhood of z, that says is the distance of this s z minus s minus delta z. That would be, again I am using the simple absolute inequalities, would be greater than or equal to absolute value of z minus s minus delta z. Since z minus s for every s on the path C is greater than d, so it should be greater than or equal to d minus mod absolute value of delta z. Now, what we have got from here, let us see. We have got that for all C, this GS is less than bounded by this number m. The denominator s minus z square, this is less than this is greater than or equal to d square, or we could say is 1 upon s minus z square, that is bounded by 1 upon d square, and 1 upon s minus z minus delta z, that is bounded by 1 upon d minus mod of delta z. So, what we have got, this complete function, that is complete integrand, this is bounded by some constant for all s on the C. Now, I will again use my ML inequality. What it says is that absolute value of this integral delta z gs upon s minus z minus delta z s minus z whole square ds should be less than or equal to mod of delta z ml upon d minus delta z d square. So, we do have that my L is nothing but the length of this path. Whatever be this length of this path, that has to be some finite number, m is also some finite number. Now, d is the minimum distance from this path from this point z to this one. So, we are getting is that this is also some fixed numbers. Now, as delta z approaches to 0, this whole right hand side, this can be made arbitrarily small, while what is the left hand side? Left hand side is your this integral, absolute value of this integral, this can't be negative, this is a positive. So, a positive quantity can be made smaller than a quantity which can be made arbitrarily small, that is it should be equal to 0. So, what we have got, this integral was nothing but the difference of, this integral is nothing but the difference of these two things. That is what I am getting is absolute value of this difference is can be made 0, or in other words what we had got from the definition of the derivative, that g dash z, which is nothing but z of z plus delta z minus gz upon delta z as delta z approaches to 0 is integral along the path C gs s minus z square ds. So, now what we have got, rather than working on a analytic function, we had worked on first thing on any path C, then I had worked on any function which is continuous only, and if I could define a function capital G such that that is integral along that path of the function gs upon s minus z, then we are saying is that function is analytic, or rather we had shown that at any point z we could define that, we could find out its derivative is existing. Now, since this derivative is existing and this z I have taken arbitrarily, it says is that in whole of this one, wherever this my function g is continuous, I would get this derivative of capital G would be existing, that says is capital G is analytic. And in the similar manner, now capital this g dash z, this is again in the form of integral of some function. So, I could say is the function gs upon s minus z upon s minus z you could get. So, again we would be having r, we just go like that one and we would be move, that is this function would again be analytic and its derivative can be given 2 times integral gs upon s minus z cube ds. So, what we have now shown, rather than just having this for analytic functions, Now we had started with a function small g which is just continuous. Now let us put to a good use of this result what we have obtained or what we want to say from this result. Let us go back to our derivative of analytic function. Suppose f is analytic in D and C be any simple closed contour in D, then we do know that fz 1 upon 2 pi I integral along this closed contour C fs upon s minus z ds. How we had find it out? This is what is our Cauchy integral formula, which says is where z is interior point of this closed contour C. We do know this one. Now here this small f, if I replace with the that our small g in the previous result, what I would get, that this fz would be analytic. This is what we are doing. We are using now. This is a simple closed contour C, and this is a point z which is interior to this C. Then by Cauchy integral formula, we do know that fz I can write as integral 1 upon 2 pi integral along this contour C of fs upon s minus z ds, where z is interior point of this one. Now this f, if I replace with g, that is any continuous function, not analytic only, any continuous function, then what we do know is that fz over here, just as there, now that would be my, this is fz would be the capital G z of the previous results which just now I had obtained. So we would get it, that is this fz would be analytic. So now what we are trying to say, that this formula is holding for f analytic. Now if this constant, this is the only thing is that is the constant, if this constant I take it as in any constant and this f I replace with continuous function only, then I would get that this f, the same f, is it alright, is analytic at z, and since this z is any arbitrary interior point of this contour, I would get that this in whole of this interior, this function fz would be analytic, and its derivative would satisfy the same conditions, that is we could, the same formula we could find out these derivatives. Now what we have actually got, we have got that rather than taking f to be analytic, if I start f to be continuous only, still I could prove that, because then what I would have, this this is any contour, and here is that the d I would take this smallest distance from z to that contour d, that is all. So we could get that all these results would be holding true. My fz would be analytic, it will have possess all the derivatives, all orders derivatives, and those derivatives will also be analytic. Now what we have got from here, we have actually proved one important result. You see, if fz is continuous in a domain D, and if the integral of fz along any closed contour C is 0 for every closed contour C in D, then fz is analytic in D. Now you see, is that is what we are trying to say. So if my D is simply connected domain, then this result is you could treat it as a converse of Cauchy theorem. How we are going to say it like that one? You see, just now we had shown that is if this is happening is that for every closed contour C in D, if this is happening, what it says is that this integral integral of this function fz dz is independent of path, because for every closed contour C this is 0, that says is whatever be this path C, this integral is 0, that says is the integral of this function fz is independent of path. If it is independent of path, then by Cauchy theorem we do know that it must possess some antiderivative. That antiderivative should be indefinite integral of this fz, that is capital Fz, or in other words then Fz would be the derivative of that capital Fz. Capital Fz is certainly analytic because that is antiderivative of this one. So, now we are having this capital Fz in the form of integral of a function fz which is analytic. So, its all derivatives would be analytic and hence it would go ahead. So, what we say is that fz is analytic. This is what we have, that is if fz is continuous and this is happening, then fz is analytic in D. This is what is we have proved. This result is known as Morera's theorem. Now, let us move one more application of this Cauchy integral formula, Cauchy's inequality. From the analyticity of the function fz, we have find it out that the derivative of f, nth derivative of f at z naught can be given as by the formula factorial n upon 2 pi I integral along the closed contour C of fz upon z minus z naught to the power n plus 1. Now, let us assume this C is any closed contour. Let us see if this is a circle centered at z naught with the radius as r. So, this is C is my z, t is z naught plus r e to the power I t, where t is ranging from 0 to 2 pi. This is the parametric representation of the circle centered at z naught with radius as r. Now, the absolute value of the nth derivative of z naught would be absolute value of this one. So, this factorial n upon 2 pi I, that is its absolute value would be factorial n upon 2 pi and then multiplied with the absolute value of this integral, that is integral along the path C fz upon z minus z naught to the power n plus 1. Now, I have taken this path C as the circle centered at z naught. What it says is z minus z naught would be r times e to the power I t, and fz is any function. So, I would simply write it out as this is less than or equal to integral of the absolute. This is now we are going with the simple result if you have done in the real analysis also, that absolute value of the integral is less than or equal to the integral of the absolute value. Now, this absolute value if I do write, this would be absolute value of fz upon absolute value of z minus z naught to the power n plus 1. Now, z minus z naught to the power n plus 1, from here I would get r to the power n plus 1 into e to the power I t to the power n plus 1. So, what we would get factorial n upon 2 pi integral along the path C of absolute value of fz upon absolute value of this one. What is the absolute value of this one? R times e to the power I t, its absolute value is r only. So, it is r to the power n plus 1. Now, this r I have chosen some number. So, f is now we are talking about analytic functions. F is analytic, that says is I could find out some number m such that fz is less than m on this whole contour C. So, this is bounded on this contour C, and by using this ML inequality I could write it out. This constant is as such, this integral must be less than or equal to m upon r to the power n plus 1 into the length of this path. Length of this path is, that is the perimeter of this circle, which is 2 pi r. What we are getting is factorial n times m upon r to the power n. So, finally, what we have got the result, we have got that absolute value of the nth derivative of f at z naught is bounded by a number factorial n into m upon r to the power n, where m is your bound of f and r is we have taken a arbitrary number, r you could say is the radius for this circle around the point z naught. Now, what it says, this inequality you would say is that is how it is going to help. This is going to help to get one more important result, that is known as Liouville's theorem. if an entire function fz is bounded in absolute value for all z, then fz must be constant. What we are saying is, in other words, that an entire function can be bounded if and only if that is a constant. That is, in a reason, if it is bounded, then it must be a constant. Let us see the proof of this one. We will use this Cauchy inequality. Fz is given as bounded, that says is fz should be less than m for all z in that reason. By Cauchy inequality, what we do get, f dash z naught should be bounded by m upon r. Now, as r approaches to infinity, that is, if I am taking r large and large, we do get that f dash z naught would approach to 0. Since that r, if you do remember, we have taken the circle around the point z naught, and that was arbitrary, that is, radius was arbitrary. So, I can make a very large circle. So, it says is that it should approach to 0, because we are saying is it is bounded and this is an entire function. So, we can take a very large circle. So, as r is increasing, I should get this is 0, approaching to 0, or rather you could say is that the derivative of f z would be 0, because this is at z naught. So, I can use it at any point z. That says is my function has to, if the derivative is 0 for all z, then my function has to be constant. So, since z naught is arbitrary and f z is entire, this says is f dash z should be 0 for all z, hence f z is a constant. What it says is that an entire function can't be bounded unless until it is constant. What this theorem is saying, I can use it in a very nice result. Let us see. I do have a polynomial of degree n. Let us write this polynomial as a n z to the power n plus a n minus 1 z to the power n minus 1 and so on, plus a n z plus a naught. Of course, a n should not be 0. Why? That is why we could say this is of degree n. And if I take this, rewrite it, I take the common z to the power n. So, I could write it as a n plus a n minus 1 upon z and so on. Since I have taken this a n to be not 0. Now, I would like to choose a large r such that for all j, my a n minus j upon z to the power j. You see here what I am getting is a n minus 1 upon z, here a n minus 2 upon z square and so on. So, a n minus j upon z to the power j is bounded by the absolute value of a n upon 2 n. What we are talking about actually, for all the z lying outside the circle with radius r. So, I am choosing a large r such that this numbers, they are, that is, I would, if mod z is greater than r, we are getting is that they are being bounded by some number like this one. Of course, why I had chosen a n, because a n I have taken that non-zero. So, this absolute value I have taken, and this n you would find it out, that is why I am choosing it a little later. If this is happening, then what? Now, I would use simple absolute value of pz and the inequality involving the absolute values. Since mod of pz would be mod of this one, which we could write mod of this first bracketed value into mod of z to the power n. So, mod of z to the power n as such I have kept. Now, see this bracketed value. This is the sum of many values. Using this inequality of absolute numbers, first I am taking this a n out. So, mod of a n minus mod of a n plus 1, a n minus 1 upon z and so on, plus a 1 upon z to the power n minus 1 plus a naught upon z to the power n. Again, for this one, again I would use the inequality. That inequality, what now I would use? Not this one, that I would use mod of x plus y is less than or equal to mod of x plus mod of y. That will give me, that is, this one would be smaller than or equal to mod of this plus mod of this and so on, and since it is the negative sign, it will again be greater than or equal to. So, I would get is greater than or equal to mod of a n, and this here this inequality mod of a n minus 1 upon z minus so on, mod of a 1 upon z to the power n minus 1 minus a naught mod of a naught upon z to the power n, and this z to the power n is as such, and this complete absolute value is outside. Now, from here, since we had assumed that for z greater than r, a n minus j upon z to the power j in absolute values, this is bounded by a n upon 2 to the power n. That says is if I take the minus sign, this would be greater than or equal to minus of a n upon 2n. So, now let us substitute this. So, this should be greater than a n is as such, this should be greater than mod of minus of mod of a n upon 2n and so on. Everything I am replacing with the mod of a n upon 2n. Now, how many terms we do have? A naught to a n minus 1, that is n terms. So, I am having this n terms like this one. N terms like this one, if I add up these n terms like this, what I would get n times mod of a n upon 2n, that is mod of a n upon 2. So, what I am getting is this is a n minus mod of a n upon 2, or that is same thing as mod of a n upon 2, mod of a n upon 2, and this is holding true when z is greater than r. Z is greater than r means is this would be greater than r. So, what I am getting is it is greater than mod of a n upon 2, and this absolute value of z to the power n we could write as absolute value of z to the power n. Now, let us see what we have got. We have got that Pz is greater than or equal to absolute value of a n upon 2 into modulus of z to the power n for all z greater than r. Now, suppose my this Pz is not 0 for any z in this whole region, then what I would get is that 1 upon Pz is less than 2 upon mod of a n into mod of z to the power n. So, this is because mod of z is greater than r. So, in this reason it should be 2 upon mod of a n into r to the power n. So, now if what it simply says is that if for all z Pz is not 0, then 1 upon Pz is bounded in the region mod z is less than or equal to r, because Pz is bounded above by in the region mod z greater than r. So, 1 upon Pz is bounded in the region mod z less than or equal to r. Hence, by Leibniz theorem says is if the function is entire and bounded, then it must be constant. So, the function Pz is not 0. So, 1 upon Pz is entire function and bounded. So, it must be some constant a which is not 0. Hence, Pz is b, because we have taken that Pz is not 0 for any z. So, whatever 1 upon Pz, that constant cannot be 0. So, what it says is that Pz would be 1 upon a, that is b, some other constant. Now, what we have got the result that if Pz is not 0 for any z, then it is a constant. So, what we have got Pz is constant if Pz is not 0 for any z, and this gives us the actually the fundamental theorem of algebra, which says is any polynomial Pz of degree at least 1 has at least one z naught such that Pz naught would be 0, because the proof you could say is by contradiction, as in the previous one we have slides we have done, that you could treat it as a proof with the contradiction, that is you can assume that P of z naught is there is no z such that P of z is 0, then we do get that Pz can't be a polynomial of degree n, then it must be a constant. So, this is the fundamental theorem which says is that for any polynomial of degree n, it must have at least n at most n roots. That is what you have done in the algebra, but not the proof. The proof is here. So, we have got one important result over here also. So, we had learned that how this Cauchy integral formula is playing magic, not only evaluation of the integrals, but in the proof of certain basic or very important results in the analysis and algebra. So, we had learned today the Cauchy integral formula, its application. That is all. Thank you.